Hey folks, so today we are going to talk about essay that two engineers, Jeff Dean and Sanjay Ghemawat from Google had written, and here my breakdown of what this means for people who want to learn performance engineering. So here are the secrets from these Google's legends. So what if I told you that two engineers wrote this document that could save your code from being 100 times slower than it needs to be? Yes, so these legends behind the Google's infrastructure recently updated their performance engineering Bible, and today we are going to break down the secrets that they don't teach in computer science classes. We have all heard the Gnuth note: premature optimization is the root of all evil. But here's what most people miss. Gnuth also said that we shouldn't pass up opportunities in that critical 3%. Today we are diving into a 40-page masterclass from the engineers who built Google's core infrastructure. Whether you are working on web apps, data pipelines, or distributed systems, these principles will change how you think about code performance. So let's get into it. First, the estimation mindset. First up, estimation. So before you write a single line of optimized code, you need to develop intuition for what actually matters. Here's the critical table every engineer should memorize: L1 cache reference, main memory reference, SSD read, network round trip in data center, disk seek. For L1, it's usually zero point 0.5 nanoseconds. Main memory reference is usually 50 nanoseconds, and SSD read around 20 nanoseconds or 20 microseconds. Network round trip in data center is usually 50 microseconds, and disk seek is 5 milliseconds. Let's make this real with an example. Say you need to sort a billion numbers. How long will it take? Will it take maybe 1 year? Definitely not. But most people would just start coding, and but Jeff and Sanjay show us the power of back of envelope calculation. A billion 4-byte numbers is 4 gigabytes. Quicksort makes about 30 passes for a billion items at 16 gigabytes per second memory bandwidth. Each pass takes zero point 0.5 seconds. That's 7.5 seconds just for memory transfer. But here's the kicker: branch mispredictions. With 30 billion comparisons and half mispredicted at 5 nanoseconds each, that's 75 seconds. Total estimate about 82 seconds. So before writing any code, you already know where the bottleneck is: branch prediction, not memory. Second, when profiles are flat, here's where most engineers give up. You profile your code and everything is slow. No obvious hotspot, just a flat profile where performance is lost everywhere. The document gives us a counterintuitive strategy: don't discount many small optimizations. 20 separate 1% improvements, they equal 22% speed up. So that's massive. The key is having stable benchmarks and being systematic. So look for loops near the top of call stacks, overly general code doing simple tasks, and high allocation counts. And don't forget the cache misses in the hot functions they have. So one Google team found code using regular expressions for simple prefix matching. By replacing rejects with a very basic string comparison, boom, significant speed up with almost no effort. 3. Memory is everything. So let's talk about the most underrated performance killer: memory layout. Modern CPUs are fast, but memory is slow, and most performance problems come down to one thing: cache misses. And here are the golden rules for that. Rule 1: compact data structures. Instead of storing pointers everywhere, use indices. On 64-bit systems, a pointer is 8 bytes, and index into an array, maybe 4 bytes or even 2. Half the memory, better cache locality, faster code. Rule 2: hot and cold separation. Fields you access together should live together. Fields you rarely touch, move them to the end of your struct or behind a pointer. Don't let cold data evict hot data from the cache. Rule 3: batch your storage. Hash maps that allocate separately for each element, that is a cache nightmare. Flash storage like vectors, much better. The document shows Google replaced nested maps with single level maps using compound keys. Massive speed up. So before, cache was unfriendly, map, you had map string data, and now it's much faster because it's map and then they have a pair, string, and data. Chapter 4, the allocation task. Every allocation costs you three ways: time in the allocator, initialization overhead, and cache line pollution. Let me show you a real example from the essay that Jebdin and Sanjay has written. A team had a vector being created inside a loop, recreated on every iteration. Simple fix: move it outside the loop and reuse it. Result: it's significant speed up. So, but here's the caveat: containers grow to their maximum size if you are processing wildly different data sizes. Occasionally reconstruct the container to free memory. Fifth, avoid work you don't need. The fastest code is code that never runs. Sounds obvious, but let's look at real techniques. Fast paths for common cases. Vector pushback usually has space, so the implementation has a super fast path that checks capacity and occasionally only calls the slow resize code. One comparison guards the common case. Pre-compute once, used many times. One team was computing graph properties repeatedly in a loop, moving that computation outside the loop 43 seconds down to 2 seconds. 20x improvement. Deferred until needed. Don't compute stats eagerly if they are rarely accessed. Lazy evaluation saves cycles. Specialize your code. The document shows custom histogram printing code that's 4x faster than general printf. Why? Because printf handles every possible format. The custom code only handles what needed. 6. The compiler isn't magic. Compilers are smart, but they are conservative. They can't assume things you know are true. Sometimes you need to help them out. Copy data into local variables before heavy use. This helps the compiler understand there is no aliasing. Move error path code into separate functions. This keeps the hot path tight and cache friendly. Use raw pointers instead of abstractions in the innermost loops. If profiling shows it matters. But, and this is critical, only do this when profiles show a problem. Don't guess, measure. 7. Parallelization pitfalls. So more threads equals faster, right? Not always. Lock contention is the killer. The document shows a case that was a bottleneck. Solution: shard it 16 ways, each shard with its own lock. Result: 2x throughput improvement. Critical sections need to be tiny. Don't do file I/O. Don't make network calls. Don't allocate memory if you can avoid it, all while holding a lock. So one Google team was acquiring a lock for every node while freeing a tree. Changed it to acquire once for the whole tree. Massive speed up. Fault sharing is sneaky. Do two threads updating different variables, but those variables are on the same cache line. The cache coherency protocol makes them fight. Solution: force variables onto separate cache lines. 8. The protocol buffer problem. Here is a controversial one. Protocol buffers are convenient, but they are slow. The document shows a test 1000 points stored in protobufs versus a simple C++ vector or struct. The vector version 20 times faster. So the advice is clear. Don't use protobufs in hot paths. If you must, use arenas to reduce allocations. Consider storing them serialized in memory. Use the view string type to avoid copies. Protobufs are great for wire formats and storage, but for in-memory computation, often a terrible choice. 9. Language specific gold mines. So for C++ developers, the document drops some real good gems. Flat hash map usually beats unordered map. Why? Better memory layout, SIMD optimization. Inline vector stores small vectors without any heap allocation. For vectors with typically 3 to 5 elements, game changer. B tree map stores multiple entries per node, better cache efficiency than STD map. These aren't exotic, they're Google standard tools because they measurably perform better. So the real lesson, what's the meta lesson from all this? The performance is not an afterthought. If you wait until you have a flat profile with problems everywhere, you're already lost. But and this is crucial, performance is also not premature optimization. The document shows a middle path. When writing code, choose the faster alternative if it doesn't hurt readability. Use inline vector instead of vector. No extra complexity. Reserve space when you know the size. Trivial change. Move variable declarations outside loops. Simple refactor. These are an optimization. They are just writing good code. Save the heavy artillery, SIMD, hand unrolled loops, lock free structures for when profiling proves you need them. 11. The measurement is everything. Here's the foundation under everything. You must measure. Guessing doesn't work. Intuition helps, you know where to look, but measurement tells you what actually matters. The document emphasizes profile before optimizing. Write micro benchmarks for hot code. Use performance counters, not just wall time. And look at cache misses, branch predictions, and memory bandwidth. One team found their optimized code was actually slower because they introduced cache misses they didn't measure. So measurement does keep you honest. So Jeff Did, Sanjay Himawat have done this thing for nearly decades. They have built systems serving billions of users. We all know that, and they are telling us that performance matters, but smart performance work matters more. So here are my key takeaways. Develop estimation skills before you code. Think about memory layout and cache behavior. Reduce allocation systematically. Avoid work you don't need to do. Measure everything and make many small improvements rather than waiting for the silver bullet. So, this document is 40 pages of hard won wisdom, and I've linked it in the description. Just go check it out. I highly recommend reading the whole thing. What's your biggest performance win? Drop it in the comments. I want to hear your war stories. And thanks for watching. And remember, the fastest code is the code that never runs. But the second fastest code is the code you actually wrote well from the start. See you in the next one.